So hello everyone. So this is a joint work with Simo Ndaoud, Adel Javanmard, and Meisam Razaviyayn, my co-authors at USC. Simo is now, he's soon going to be back in France, probably, but I don't know. But most of all, it's really work with Simo, the technical part at least. And so to give you a short preamble, this is a very nice and I think cute statistical testing problem, which seems to be a bit overlooked. And it has a flavor of a two-sample testing problem, but it's not exactly two-sample testing. It has a trick inside. I will start with the general problem formulation, which kind of which gives you, it's probably like the best way to state the problem so that you can pick your interest and just think about it. And then I will go like most of the talk, the technical part of the talk will be focused on the case of linear models. The case of linear models, we understand, well, we have nearly matching upper and lower bounds for this problem. And then I will go over one extension. So there are basically two extensions that we consider from the case of linear models. One of them is bulky. And hello? Are there any problems? Sorry, there was somebody. Okay. By the way, can you hear me well? If somebody, yeah, okay, hopefully can. So yeah, so there are two extensions from the case of linear models, and one of them considers generalized linear models, and the result there is technical, and I won't present it here. You can check the paper. Another extension is the asymptotic result for the general case, and this one I will try to just describe, at least to present it. So let's start. What is the general problem? What we call model discrimination. Maybe it's not the best name. So let Z in subspace, big Z, calligraphic Z, be a random observation. There are two possibilities for the distribution of this observation, either P0 or P1. Okay, so let me tell you to begin with that P0 and P1 are not known. Let me assume that there is some strictly convex loss function, L of theta Z, so its convexity is with respect to theta, so theta is a parameter vector, so it's a parametric loss function, the randomness controlled by Z. And I can consider two population risks related to these two distributions. So I average my loss function over one of the two distributions. Then, because of strict convexity, I can, well, actually, okay, I need strict convexity and I also need existence of the minimizer. So if it exists, it's unique. So let's say that I just assume that the minimizer exists and is unique. I call it theta K. Theta K is the population risk minimizer corresponding to P0 or P1. Now, what I know as a statistician, and this is the tricky part, I know theta star, which is either theta 0 or theta 1. So somebody just showed me theta star. Okay, and they didn't show me the other guy, which I call theta bar. I call theta star the actual model and theta bar the complementary model. So sorry, LZ should be, it's a typo, should be L of theta Z, so Z is dark. And I observed two samples. I observed the sample, ID sample from P0 and P1. And what I want to understand is I want to understand which one of the two is theta star. So in other words, I need to test, so theta star is something known, and I can awkwardly write my two hypotheses this way. Any question? Oh, Okay, it probably was a glitch. But the point is that actually theta star is known, and theta 0, theta 1 is the aggregated unknown parameter here in R2D. Let me restate this a bit. So let me contrast it with a classical setup, the classical kind of prototypical testing problem. I have one sample Z corresponding to some parameter theta. And I have two possibilities, theta 0, theta 1, which are known. So I observe only one sample, but I know two parameters. And I need to guess the theta that generates the sample, which one of the two values it is actually, theta 0, theta 1. In other words, I have two simple hypotheses about the unknown parameter theta in this setup. Now, in our setup, we observe the two samples, but only one theta star, which is either theta 0 or theta 1. And I need to understand which one of the two samples corresponds to this theta star. Or, in other words, I'm testing two composite hypotheses about the aggregate parameter theta 0, theta 1. So why I'm interested in this, we will at some point discuss it, but let me for now just not focus about it. So I can just ask about this problem per se. I think it's interesting enough. So what are these hypotheses, these two composite hypotheses? Well, as stated right now, the two hypotheses are just H0, the null is that theta 0 is equal to theta star. Theta star is given and known, and theta 1 is something else. H1 is theta 1 is equal to theta star, theta 0 is something else. Of course, this is ridiculous because then the two parametric sets, they just intersect. So the problem is not well stated. We have the intersection of two hypotheses of two parametric sets. I don't want to work with this. So instead I say, okay, I need some separation. I need to separate the two sets. Well, what is the right notion of separation? Long story short, what we think is reasonable here. Oh, by the way, just to note that, of course, this is the bad case, right? The degenerate case when theta 0 is theta 1 and just theta star. So they just intersect, and it's not nice. The problem is just pointless because there is this point which is at the same time corresponds to the two hypotheses. So how do I separate the two sets? So essentially, I don't want this problem to depend on the parameterization. So I want it to be characterized in terms of the prediction quantities and not the estimation quantities. And so I just say, okay, let me assume a priori that theta 1 and theta 0 are separated in terms of the excess risks. So I will just say that the excess risk, there is some delta 0. It's let's say the lower bound, or actually the value of the excess risk of theta 1 with respect to theta 0. Well, with a corresponding distribution for which theta 0 is the minimizer. Similarly for delta 1. Delta 1 is the excess of theta 0 over theta 1. And then I can just say, okay, I'm interested in this problem. So I know a priori that theta 0 and theta 1 are separated as follows. And also my two hypotheses is that theta 0 is equal to theta star or theta 1 is equal to theta star with the matching sets for theta bar for the complementary model according to this separation assumption. I don't even need to formulate the sets. So what will be my task? My task is to characterize the sample complexity of distinguishing between H0 and H1 with fixed probability. Say 2/3 or whatever, bigger than 1/2. So it will depend on the two separations and probably dimensionality in some way. So in other words, the sample complexity is the smallest sample size. So here I assume for simplicity that the samples are of the equal size, which is sufficient for the errors of both types to be bounded by 1/3, let's say. Any questions if there are at this point?
But what are exactly your observations?
So essentially within this talk, I will first consider linear regression starting from the next slide, where Z will be the pair of design, random design, and Y. And it will also be well specified. Then I will talk about the asymptotics, but for the general case where Z is whatever. So it's just a parametric family. Also in the paper, we consider generalized linear models with misspecification. And it's kind of moderate misspecification. It's not whatever misspecification. So in some sense, bias should be comparable with some notion of variance. But this I will not discuss in this talk. It's the technical.
You said you observed theta star.
Yes.
But how do you observe it? Is it perfectly or with some error?
That's a good question. So essentially, there is theoretical analysis that just say that theta star is something that is known to us as a tester, and we can just use it in the test statistic. But then if you look at our actual test statistic, this actual test statistic, if you can actually compute Fisher information that it carries about theta star, and it's going to be O of 1. So essentially, we have like O of 1 measurements, like scalar measurements, and that essentially the point is that your test statistic actually doesn't reveal much information about theta star, and this is very important. All the applications we have in mind, they exploit this. This is what we actually started thinking about completely, and then there was this kind of model discrimination or whatever. Okay, so let's talk about linear models. Let's keep things specific. So consider the well-specified. So let me just formulate the setup of a well-specified linear model in that language. So my observation Z is an RD plus 1. It's a pair of X and Y. It's a random pair X and Y. X is the design. My loss is the squared loss. So X transpose theta minus Y squared. So the two distributions, PK and K, in this talk is always binary, corresponds to the two hypotheses. So PK, P0, P1 is that X has covariance is zero mean with covariance sigma K, and Y is X transpose theta K plus Gaussian noise, standard Gaussian noise. I scale the variance of the noise here to sigma. So if the variance is known and the same for the noise, I can always, or actually if it's known and not even the same, but if the noises have different variances actually after the two hypotheses, we can just rescale. But if the variance is unknown, I will just say that in the paper we consider adaptation to this. So don't be concerned too much with Xi having unit variance. And if you are, look at the paper, please. So then let me just write the two samples in this form, right? So big ZK is the XK, YK, where XK is the matrix N times D. So with rows corresponding to observations, and YK is the vector of responses for two hypotheses. So sigma K will be my covariance, and I also have the sample covariance, so the empirical counterpart of sigma. And also I can introduce the population rank and the empirical rank, so the rank of sigma and the rank of the sample covariance. So in these terms, actually, I can write my separations. So the separation is the excess risk for the well-specified linear model, right, with quadratic loss. So it's going to be probably 1/2 is missing though, but okay, 1/2 is missing, I think. Theta 1 minus theta 0 squared in the Mahalanobis norm of sigma K. And then I also have what I call delta K hat. It's the random estimate of delta K, it's the empirical separation, where sigma K is replaced by the sample covariance matrix.
Can you compute any of them, or you?
No, you can, but it's fine. It's fine. They're used in the analysis. You don't need them in the testing procedure. This
so
is
because
just
you only know theta star, yeah?
Yes. You know theta star, you know the samples, but you don't know theta 1 and theta 0. I mean, you know one of them, right? But you don't know which one anyway, and you don't know another one. but you don't have to compute them. This is just to analyze the procedure. So now let me consider a basic test procedure, which you can compute, basic test statistic, and which is suboptimal to my big surprise. I mean, now from the talk, it's going to be obvious, hopefully, that why it is suboptimal. But when we were looking at this, it was a big surprise for us, to be honest. So, so the idea is very simple. You try to guess which of the two samples is better fit by theta star. So let's compare the two errors, the two empirical risks. So I can just compare the squared norm of y0 minus x0 theta star, which will be just the same as the quadratic risk of the first sample for theta star. Theta star I know, right? So I essentially just evaluate the prediction quality of theta star on one sample and the other sample, and I compare. Okay, so if on the 0 sample it's more error, the error is bigger, that means that I'm gonna have 1 in this indicator, so this procedure tells me H1, accept H1. Now, I put here minus n formally. And now this minus n is just like, why did I put it? But actually, it's clear, like it's going to be clear in a second why I put it here. So let's try to analyze this procedure. So hopefully I convinced you that it makes some sense. Now let's try to analyze what's going on. So under H0, without loss of generality, let's say H0 holds. Theta star is equal to theta 0. Then that means that in the left-hand side, the squared term was going to be the square of the noise. So it's a chi-square with n degrees of freedom. And the right-hand side is going to be the cross term. So it's going to be chi-square with n degrees of freedom plus the cross term plus the kind of the offset term, what do you call it? Offset term, which is the squared norm of theta 1 minus theta 0 related to x1. So actually, well, that means that the expectation of the left-hand side is 0 under H0, and of the right-hand side, because the cross term conditionally on x1, the cross term is 0 mean. So my model is well specified, right? So that means that if I fix x1, xi1 is still Gaussian, independent Gaussian. And the right-hand side, well, it's going to fluctuate around n delta 1 hat. So this is because if you remember this delta 1 hat had 1 over n ahead of it, and here there is no 1 over n. Great, so I just rewrote delta 1 hat. So this kind of motivates the test a bit more precisely. So we see that the type 1 error happens when the random fluctuations, the center fluctuations, which are these fluctuations plus these fluctuations plus these fluctuations, go over the offset term, which is a constant. I mean, it's not mean 0. It's conditionally on x1. It has n delta 1 hat average. Any questions? Any questions now? Okay, feel free to use chat for the questions, by the way. Okay, so now let's be a bit more precise. We can just compute what will be the error probabilities here. So essentially, I repeat all my observations before. I just say, okay, left-hand side under H0 is the centered chi-square. And this is why, this is why I subtracted n, right? Any questions? Okay. And the right-hand side has also the cross term. The cross term conditionally on x1 is Gaussian with this variance. And there is also this non-random guy. So I do my arithmetics. I do my Gaussian bound and chi-square bound. Well, I even wrote two-sided chi-square here, but it's fine for this calculation. So the point is that I have the chi-square. Now, please pay attention to this, okay? This is really important. The chi-square, how I can decompose the error. So the error of the first type, right, is when we accept 1 when actually H0 held. So in other words, when fluctuations are bigger than n delta 1 hat, right? Well, if I split the n delta 1 hat into 3 parts, so I'll have the chi-square fluctuations of the right tail, then the left tail of chi-square, and then the Gaussian guy. So if you do the computation, what's going on is that there are two terms here. There is one coming from Gaussian and the sub-Gaussian tail of chi-square. Or actually, no, sub-exponential tail of chi-square. And there is another one with different structure coming from the sub-Gaussian tail of chi-square. So one of them, the first type, which is kind of dominated by the Gaussian behavior, is this guy. So the error here of this term is controlled as, by exponential of minus n delta 1 hat. Now the Gaussian guy, because in this bound in the sub-Gaussian part, so like v square over s, s explicitly enters here. S is the number of degrees of freedom of chi-square. So in this case, this is chi-square with n degrees of freedom. So I take my v, the deviation, which is n squared delta 1 hat square, and I divide it over the number of degrees of freedom, which is n. So as a result, what I have is exponential minus n delta, the minimum of delta 1 hat and delta 1 hat square. Now, you know, I can omit the details. I can condition over x, over the distribution of x. If x is nice, essentially my delta 1 hat will become delta 1 up to some constants and tricks. So the behavior here will still be this. So what do we learn from this? Well, under the very mild assumption that delta is at most 1, because actually if delta is bigger than 1, it's roughly like 1 sample is enough anyway, and there is no problem. Then delta square will be smaller than delta. And so my error is actually minus n delta squared. And so my sample complexity is 1 over delta squared. Where delta square is itself here, the delta without index is kind of the worst of the two deltas, because one delta appears in the error of the first type, another in the error of the second type, right? So I need to kill both. It's 1 over delta squared. To move forward, I really need to be sure that anybody who wanted to understand it understood it.
Okay. Yeah, it's clear.
Thank you. Now, how do we improve over it? Okay, so essentially you need to, it's kind of clear from this analysis that here we lose here. So this term had a different behavior than this guy. There was a possibility to exploit this n square here, which would drive the error faster to 0. The problem was that the number of degrees of freedom was too large. And so n square was killed back to n. So long story short, there is a way of doing exactly this, of reducing n to the minimum of n and the rank. So let me consider this test, which will be a nearly optimal one. So before measuring the squared norm of the residuals, I will take the projection over the corresponding signal space x0. So let P of x for x in R and D be the projector on the column space of x. So it's the projector on the subspace of Rn. So it operates in the space of residuals, in the space of, response, not in the space of parameters, but in the space of responses in Rn. And I compare, so my previous interpretation told me that what I was comparing actually were not the errors, but the fluctuations of the error around the mean, and actually around the conditional mean. So I will do the same here. But now my conditional mean under the matching hypothesis for this guy and for this guy, I actually R0 hat and R1 hat. So R k hat is the rank of the empirical covariance. And if you essentially, if you substitute here the matching theta star, so like theta star equal to theta 0, you will have that we project, for example, here psi 0 on the subspace of dimension on the subspace spanned by the columns of this matrix, but its dimension is actually the empirical covariance rank with probability 1 conditionally on the x. So kind of this testing procedure should be thought as something conditional on x0 and x1 with Gaussian in the noise because of the well-specified model. And here just a very simple kind of calculation, verification that indeed the dimension of this column space is actually the rank of sigma hat. So it's kind of a direct calculation using the permutation properties of the trace. Oh, and by the way, here, this means that it's a generalized inverse of a PSD matrix. So every time I use this symbol, inside there is a PSD matrix. So I just take the eigenspace corresponding to the non-zero eigenvalues. Okay, so let's look at this improved test. So again, I consider H0 without the loss of generality. Now I have that I condition over the whole design, over the entire design. So conditionally on x0, the left-hand side is distributed as chi-square, center chi-square with R0 hat degrees of freedom. And on the right-hand side, there is the chi-square guy with R1 hat degrees of freedom, and the same as before. So for the cross term did not change because we essentially the cross term anyway projected on that subspace. It was spanned by the the cross term correspond to x times something. So there is already the combination of the rows of x. And right, so then I say, okay, I can just do the same calculation as before, but I will use that with probability 1 over the design. RK hat is actually the minimum of RK and N. Yeah, any questions? Okay. Yeah, so basically, yeah, so this is what gives me the reduction, right? So I see that I will always, my number of degrees of freedom will always be smaller than the sample size, of course. Well, because of course I projected, right? So I was projecting on the subspace of the dimension RK hat, which is the empirical rank. Well, the empirical rank will be, before I sample enough samples to possibly get out of my subspace, I will have N equal to RK hat simply. But as soon as N is bigger than the actual population rank, my projection will not be void anymore. I will project inside on the subspace. The signal space will never have the dimension more than RK, right? And actually, this is kind of, well, this property, it holds for the Gaussian design, of course, but also it holds for, essentially it holds for the design that has a density on its support. And even in the discrete case, you can prove there is kind of a combinatorial calculation, for example, for the design, which is a random, essentially when you sample from the words. So for some like simple discrete design, this also holds up to some constants, but it's fine for this kind of things. So essentially what happens is that I conditionally analyze my error. I have this. So my N degrees of freedom became R0 hat and R1 hat. But R0 hat and R1 hat are the minima with probability 1 of RK and N. And if I do arithmetics, I have this. So essentially, again, I can average out the design, and I emit it here. But the point is that what I will get is the exponential of the minimum of n delta, and instead of n squared delta square over n, as before, I now have n squared delta square over the minimum of n and the worst of the two ranks. Again, the worst because, and the delta again is the smallest because I have to look at the two types of error. And so finally, I can just tell you that this is actually not directly obvious to me. It's some kind of juggling with formulas, but the point is that under, again, a very mild assumption that delta is at most a constant, this bound on the probability is equivalent to this bound on the sample complexity. So it's not immediately obvious because here's the proof, but it's true. So your sample complexity is the best of the two things, 1 over delta square, as for the basic test, and the reduction which is rank dependent. So it's square root of R max, the worst of the two ranks, over delta. So what we see is that the complexity doesn't depend on D per se, of course, on the dimensionality of theta, because this is kind of, this is kind of an estimation quantity and not the prediction quantity, strictly speaking. But okay, it depends on the ranks. But it depends on the ranks in this way. So any questions?
Can you do it with effective rank or something like that?
Right. So here right now, this is the actual rank, and this is a well-specified model, right? But even in this talk, we will see that we will have the notion of effective rank appearing instead of R. For the it will be for the asymptotic result for the general case. Also, again, there is a notion of intuitive notion of effective rank appearing in our analogous results for the GLMs. So if you ask me whether I can just write here the effective rank instead of the actual rank if I have a Gaussian linear model without misspecification, the answer is yes.
Thanks.
But it follows from in any case, it follows from the GLM, from our GLM result. I honestly just don't remember right now whether we have it separately for the Gaussian case. I think we don't. Yes. So here, the setup is that you have two samples of the same size. You can consider also different size, but here it's the same for simplicity. And you ask what n allows you to separate the errors of both types from 1/2 by a constant margin. So let's say to make both errors less than 1/3. It's actually, as soon as you do this, you can do boosting, right? You can just like sample split if you know the sample complexity and do any probability of error. And also you can do a kind of, well, it's another thing, it's not directly related, but you can also do majority vote to make things robust here. So as soon as you have, so essentially the result we have for GLM, it's actually under finite moment assumptions. And the way we establish it is that we just work with the fifth probability of error, and we use the standard like inequalities without sub-Gaussian assumptions, with finite moment assumptions, and then we just boost. We just say, okay, we have finite probability of error. Now we have any probability of error by repeating the test. So it's testing, it's not estimation. That's why these things are easy here. Not prediction or estimation, just testing. Okay, any more questions? Like, it's not like I can, we can go through this proof, but it's just really some juggling, completely formal, juggling with formulas. You won't learn anything new. You can just believe me that this is this, or check it if you want from this. Okay, I think let's go next. So let's compare with a basic test. So, so first of all, I already mentioned how the two sample complexities compare. So this projection allows us to improve over the 1 over delta square sample complexity with a rank dependent term. Okay, so moreover, I can conclude that there are essentially two regimes here. What I call well-separated regime and the non-separated regime, right? So in the well-separated regime, delta is big enough. Namely, it's it's at least 1 over square root of the rank. So, okay, now I have to think. I don't remember that. So if delta is bigger than 1 over square root of R max, then this thing will be bigger than this. Wait a sec. So 1 delta square is smaller. Yeah. So it's 1 over delta, and then it's 1 over delta compared with. So yeah, so 1 over delta square is smaller. So the complexity is achieved on 1 over delta square. So in other words, in the well-separated regime, your bound stops depending on the rank. Your sample complexity depends only on the distance. And moreover, 1 over delta square in this regime actually will turn out to be smaller than our max. Smaller than the largest of the ranks. Now, if I say that my ranks are actually of the same order, okay, so let's say our mean is of the same order as our max. So for something to be smaller than our max, it's the same up to a constant then for it to be smaller than our mean. What happens is that n is smaller than both of the ranks, and I don't need projections. So to perform according to my sample complexity, I actually can already do this with a basic test because I don't need projections, which is what should be expected because we are in the regime where this bound is active, right? Where 1 over delta square sample complexity bound is active, but this is the bound for the basic test. However, for the ill-separated regime, when delta is smaller, this guy becomes active. It's smaller than this. So we start to gain because of the Rmax, because of the ranks. But to have this gain, we actually do need to project. So the sample complexity here is bigger than the ranks. But when the sample complexity is bigger than the ranks, so n is bigger than R0 and R1, then the empirical ranks are equal to the population ranks, and they are smaller than n. So the corresponding signal subspaces have dimensions smaller than n, and I do need to project. In my improved test, the projections are not void; they are really there. So that's pretty much sums up what's going on for the upper bound. Then just a small interpretation. So essentially, you can interpret this. I don't know how much it is interesting, really, but let's just briefly go over it. So you can interpret this improved test in terms of the plugin estimates, in terms of the kind of ill-posed plugin estimates of theta 0 and theta 1. So this is a bit tricky. And of course, this was deduced after the result was figured out, because essentially we tried to explain to ourselves and the reader, like what are actually theta 0 hat and theta 1 hat, how do they connect to this procedure? Because the point is that here the sample complexity can totally be smaller than the ranks. If you think about it, right, in this regime, you don't have prediction estimates of theta 0 and theta 1, of course, right? It's like your sample size is smaller than the dimension of the subspace, of the signal subspace. And this is the right answer. Okay, that means that no chance that these things are even uniquely defined. They are not actually. So you can just write the normal equations and say that theta 0 hat and theta 1 hat are arbitrary solutions to these equations. And then you can actually express the squared norm of the residual. It turns out that by some massaging, it's this. It's what you measure is the squared distance respect to empirical covariance of your plugin estimate minus theta star. The plugin estimate is not unique, but in this space, okay, of sigma hat, it is unique actually. And this is what you measure. So you actually compare this guy with its average over with its expectation under the matching hypothesis, conditional expectation, conditional over x0 or x1 here. And if you rescale by n, so it's the same test, this is what you actually compare. You compare the fluctuations of the two guys against their conditional averages. So this is kind of just a nice, cute interpretation, another interpretation of what's going on. And now I will kind of teach the idea for applications, and then in the end we will look at applications if time permits. So how we actually started to think about, we were thinking about the following. Can you test the identity of theta star without being able to recover theta star? So in all this story before, theta star, I said theta star is known to the statistician, right? But actually, if you look at our test statistic, for example, here, right? Well, theta star is accessed by, like, 4 scalars at most. It's like really a constant number of some measurements of theta star that our test accesses. So it doesn't really need full access to theta star. Well, okay, you can also say, well, but I observed the 2 samples and one of the 2 samples allows me to learn theta star. Well, yes, that's true. But the thing is that what is your sample size? So your sample complexity is this. But what is the sample complexity, even if somebody told you the right sample? So you already know the identity of whether theta star corresponds to the Z0 or Z1. How can you estimate? What is the sample size to estimate? Well, at least you need this. So to estimate, let's say, well, roughly, okay, you need the rank over delta. So to estimate each of the 2 models, theta 0 and theta 1, up to the prediction distance delta, you need the rank over delta samples. It's what I'm saying is just linear regression, prediction error for linear regression, not more than this. But this is way larger than our thing. Well, there is again the R mean against R max story, but I don't want to go into this. So the point is that testing here turns out to be possible without direct access to the model theta star. And even if you have the samples themselves, and not only the measurements, not only the test statistic, still your sample sizes do not suffice to recover theta star and theta bar up to the kind of the natural measure of recovery between them. So up to delta. Which is nice. I mean, it's kind of a standard occurrence in statistics where testing turns out to be easier than estimation, but we really started thinking about applications here. And we actually wanted exactly this property from the procedure. We ended up with it. We'll go to the applications in the end. But this is what I kind of call a non-disclosure property. So we can discriminate between the 2 hypotheses without recovering, well, for example, the complementary model in the case where we are just having the direct access to theta star. But actually, you can say that even if you're, as a tester, you don't have direct access to theta star, you have access to the samples Still, this is not enough to recover theta bar nor theta star. Probably better to discuss this when we deal with applications, because it's probably way too abstract right now. Let me just briefly go over the lower bound. So for the lower bound, essentially we need to lower bound the sum of the two errors, the first and second type. So we use the standard minimax setup. We fix one of the covariances to be rank R. What we do with the other covariance, don't remember it now. I think here we can even establish it with the, so we already find with another covariance being the same for the lower bound. And essentially, long story short is that we have the gap between the upper and lower bound. And this gap is that instead of delta mean, we have delta max in the lower bound. And instead of R max, we have R mean. We think think the upper bound can probably be improved. So just briefly, let me just briefly tell you how to show this. So essentially, you need to prove two bounds separately. One is rank independent, another one is rank dependent. So for the rank independent part, it's easy. So you say, okay, I can consider an easier problem where theta bar is known. So I know not only theta star, but also another model. And my two hypotheses are then simple. So it's theta 0, theta 1 is equal to theta star, theta bar, or the other way around. Theta bar is something fixed, and it's fixed on the so that it's on the distance. It's on the distance prediction distance delta from theta star. Okay, so now intuitively this will lead me to the rank independent bound, because now everything happens along one direction, right? So there is no dimension in the problem anymore. It's just measuring distances along one direction. This is what happens. So I just do the likelihood ratio test. I know that it's optimal by the Neyman Pearson lemma with respect to the sum of errors, and I just look at its conditional error probability, and I recover what I need to recover. Now for the rank dependent part, it's actually technical, so you put the Gaussian prior. Then you have to lower bound the bias risk, and then you massage. You massage, and you do by the Neyman Pearson lemma. You just really need to lower bound the bias risk, but then you actually need to do some technical lower bounding, and you're done. I don't have any simple explanation, and to be honest, it was quite surprising to us why it is so technical here, but it is. Yeah, so now, Nikita, answering your question, beyond the linear models. So let me just briefly announce what's going on, and then we'll go into some details. So essentially, we consider the asymptotic regime where the sample size goes to infinity, whereas R0, the two ranks are fixed, and delta goes to 0, so that n delta scales to constant. This is the right scaling, because if you look at first of all, it's the right scaling because then you just apply the central limit theorem directly, and the proof is kind of quite easy. I mean, it's essentially some central limit theorem plus massaging, okay? But then another reason why it's natural is because if you actually look at the previous bounds on the probability of error, then it was n delta, the whole aggregate, the whole product that entered, and not n and delta separately. So it's natural to just say that now n delta is something which we call lambda, and it converges to a limit. So then essentially what we show, high level picture, is that the upper bound is this, the exponential, the probability of error, the exponential of the smallest of n delta and n delta square over n squared delta square over the worst of the two effective model ranks. Now the devil is in the detail how you define the effective model ranks. We will look right now on the asymptotic result, and then there is a generalizing in your models where kind of you have a similar flavor of the result. Open questions, first of all. How to close the gap for linear models between the upper bound and lower bound that I mentioned. Second, we will look at the asymptotic result, but what would be the non-asymptotic way of proving this? Then, in applications that we will again consider briefly, essentially, you really kind of tend to work with the distributions that are mixtures. So somehow in the applications that we have in mind, one or both of the distributions P are actually mixtures, and whereas our upper bounds apply, the lower bounds don't apply. And so one can possibly do better knowing the structure. So would be interesting to look at this. And what can be learned about the two-sample testing? So there is, okay, so let me just briefly mention what is two-sample testing. Two-sample testing is the problem where you are given two samples, Z0 and Z1 in our terminology, and nobody told you theta star. They just ask you to check whether the two samples correspond to the same distributions or the two different distributions. If you look at the, well, actually the paper that kind of seems to be solved, this problem was brought up by Barrois in 2003 or something like this. Recently, there was a work with random design. So Barrois considered the case of orthogonal design. So the question of design goes, it's kind of eliminated. But we see from this kind of story that randomness of the design can actually be something that can be exploited here. The result I know for the random design, it's a recent paper by Blanchard. And essentially, it shows this bound. So this guy is here, the corresponding sample complexity with the rank dependent term. But the rank independent term is not here. So kind of intuitively, if somebody told you theta star, they gave you a hint. Okay, so, and this hint allows you to get a better complexity of this term. So in some regime, it allows you to be rank independent. But there might be different setups to sample testing. For example, I started looking at the setup where you have the same mean in the design and non-zero mean. And when you resample, the mean stays the same. And then you can kind of try to exploit the fact that the mean of the design is the same with time. Now, in the remaining time, let me just briefly go over the asymptotic result or go over the applications, actually both. Do I have 7 minutes more? Okay. So first, the idea for the asymptotic general results. So the hardest thing was actually to figure out the test statistic. Okay, so that was some insight. Now it will seem again completely logical. So let's start. So again, so now it's a general situation where there is some loss L, and there is a corresponding empirical risk, which I call LK hat. So it's the loss related at theta on a sample big Z K. So this is its gradient, and that's the empirical Hessian at any point theta. So now my Hessians are not flat, so they depend on theta because it's not the quadratic case anymore. Let me introduce the two matrices. So HK is the Hessian matrix and its empirical counterpart, and also GK is a Fisher type matrix. Okay, so it's the covariance of the gradient at theta over the pk distribution. So I know that in the well-specified case, I have this. So this is called Bartlett identity. So I have the two matrices are equal at the population minimizers. Otherwise, I can just introduce the standardized Fisher matrix. So I can rescale G by the HK. It's my way. I don't know it might be the standard nomenclature that I don't follow, but I just used to write things this way. And I can introduce the effective rank, which is just a trace of this guy at the population risk minimizer. So if in the well-specified case, it's just going to be RK, the rank of the Hessian. Otherwise, it's I can just call it differently, but hopefully this will be something similar to RK if the misspecification is not too crude. Now, I really want to figure out my test statistic. So I know that in the Gaussian case, this is my test statistic. I also know that I have this kind of zoo of objects here, like Hessian, gradient, empirical counterparts, blah, blah, blah. So I look at this guy, okay, and I say, okay, I rewrite the projector guy this way, and the residual, I put the X from the residual here. And then I also write formally my quantities, the gradient and Hessian for the linear model. And recognize that actually in the case of the linear model, I got this guy. What I was looking at was actually this aggregate. I looked at the squared norm of the gradient of the empirical risk at theta star. And the norm was the dual norm of the Hessian. Actually, the pseudo-inverse guy. So this is the Newton decrement, right? So this is the Newton decrement of the sample corresponding to this empirical distribution evaluated at theta star. So actually, what I have to compare, in my test statistic, the empirical, the fluctuations of the empirical Newton decrements for the two samples, how they deviate from their expectations, their conditional expectations under the matching hypothesis. The problem is that I don't exactly know these conditional expectations, but actually in my asymptotic regime, I kind of know them. I can just replace them with something that I can compute with their unbiased estimates that can be computed from the data in this form. The point is that here I'm able to use theta star in both cases. I don't need to know theta 0 and theta 1. The reason I'm allowed to do this is actually because delta goes to 0 in my asymptotic regime. And so theta 1 goes to theta 0 in the right space. So you can prove, it's not hard to prove that this test has the promised error bound, where rho max is the worst of the two effective ranks. And then we kind of do a similar thing for generalized linear models, but it's way more technical, and I don't want to. It's an hour enough, but I will be happy to discuss it offline. There is some technical work there, but you can prove results with weak moment assumptions and with misspecification. And now about applications. So very briefly. So consider the following protocol. There is a learner, what we call learner. Think of learner as Google, like Fang, a big company. The learner has a very big data set, and they train a prediction model. The very big data set will correspond to our population distribution, P star. Because it's a very big data set, so we just think about it as the whole population. We don't care that it's discrete. And now I have to test the two hypotheses. So essentially, I am, as the testing entity, I'm called the auditor. And there are two kind of variants of this protocol. I can either be separate from the learner. Let's say I'm kind of the external arbitrage entity, okay? Or I can just be a subdivision of the same company. So the difference is that in one case, I have access to the samples, and in another case, I don't. So the point is that we can exploit the sample complexity property, the non-disclosure property that says that the sample complexity of testing was way smaller than the sample complexity of recovery to guarantee some non-recovery properties. So I will be able to test to identify theta star learner's model without being able to recover learner's model, even when I am given samples from the two distributions, one of which corresponds to this model. Just because, essentially, just because the samples are too small. They are large enough to allow me to identify theta star, but not large enough to allow me to learn it. So for the model, it's good because for the model, theta star, for the learner, it's good because for the learner, theta star is a proprietary model. So the learner wants us, auditor, to be able to identify what theta star is, but it doesn't want us to be able to recover. Well, how can this protocol be used, right? So what is the protocol? Well, I decide as the auditor what are my sample sizes. They can even be different. If I have implemented the sampling oracles for the two distributions, then I just feed my sample sizes to the sampling oracles. They generate me 2 ID samples of these sizes, and then I ask the learner to evaluate its model, well, to compute the Newton decrements, basically, corresponding to its model only theta star on the two samples. Then, as the auditor, I either just compare the two numbers, essentially, the fluctuations of the two Newton decrements, or I can even have the two samples and compute everything myself. Now, let's look at the two applications. So an easier application and a more complicated application. So an easier application. Probably less useful, but easier to explain. So let me have a population of Democrats and Republicans. Okay, and I have a data set, and I want in this data set for them to be fairly represented. So my data set should have half of Democrats and Republicans. So I don't know, men and women, for example. Or not half by half, but some given proportion against the other, whatever. So I will define H0 to be the 1/2 mixture of Democrats and Republicans, and H1 to be some shifted mixture. So if I know this, how much H1 is different from H0, so what is delta? If I have sampling oracles for P0, for the Democrats and Republicans, so if I can sample from the pool of Democrats and Republicans, then I can also, by just mixing these two samples, I have sampling oracles for P0 and P1. If there is some model that is learned on P0 or P1, I will be able to guess on which one it is learned and check my hypothesis. So this is less interesting, but pretty easy. This is way more complicated and probably way more useful. So here, what we call testing for data deletion. So my big company, I don't know, Facebook, is the learner on this protocol picture. It trained a prediction model theta star on a very large data set, P star. Now, there is this legislation, right, recently that has been guarantees that if you are asked to delete your data from a company, the company should do it. And the trained model shouldn't be using this data anymore. So ideally, they should be retraining their model or have some methods allowing to adaptively exclude the, maybe they don't want to run the whole training process again, but there are actually some techniques for removing the influence of given data points from the learned model. So we would like to test whether the company complied with this. They might be lazy to do it, or they might not want to delete half the data, for example, for some reason, if there was a massive breach. They might not want to give up the data. On the other hand, they probably want to demonstrate that they comply with these requirements. But also, while demonstrating this, they don't want to reveal their model. This is their market value. They don't want us to be able to just recover theta star. So what we do is that assume that we have the whole, explicitly the whole set queue of deletion queries. So there are all data points of all users has to be deleted. We can even sample from it, but let's say we even have them explicitly. How can we use our testing to this testing framework to check whether they removed Q from their sample, from their data set? Where well, H0 will be the clean data. Let's call it the corresponding distribution P0. And let's say that I have a sampling access to P0. So from the clean data, I can just sample a small subsample. Note that this is a reasonable assumption because essentially I can just ask the company and they will just give me sampling from P0. Either they actually train theta star according to P0, so either they behave nicely, right? So they actually deleted the data. Then this is just their sample. Or if they misbehaved, they will definitely not include any data from Q, because then we will just run it against our Q and see that they're like bullshitting us already. So then having Q and having sampling access to P0, I also have sampling access to P1 by just considering this mixture. If I know what is the fraction of Q in the overall dirty data set. Right? And then I can just run my procedure. And the point is that from Z0 that I have as a tester, this auditor, I don't require the direct access to theta star on the company. I just require a subsample of P0 and P1 that I can generate from the first subsample. They will be enough to run the testing procedure to test H0 against H1, so clean data against dirty data, right? Without being able to recover theta star, because my sample sizes will not be enough. This is something with which we started. Okay, so now there is a catch, of course, that here the distribution is a mixture. So it's really not linear regression at all. At least not a well-specified linear regression. But at least there is some approximation of the theory to this setup. I'm done, I think. Thank you.
Okay, thank you. Any questions? Do you have any ideas about asymptotic results?
Sorry, about what? Yeah. Yeah. So we have, it's kind of, we have two extensions that don't join really. So the thing is that our non-asymptotic results that we currently have, apart from the case of linear models, they concern GLMs. And in GLMs, as in linear models, there is a clear separation. There is design X and there is Y. And the thing is that this testing procedure really, in the case of the linear model, it's kind of, it really uses conditioning over the design. Whereas in the asymptotic case, it's kind of, it doesn't make sense to even ask what it is, because essentially you kind of conditional distribution, you don't care about it because the sample size is very large essentially. So to get non-asymptotic results, well, we can probably go from the GLMs that we have with canonical parameterization to GLMs in a more general sense, kind of really generalized linear models in the sense that generalized linear prediction models, okay? You're trying to predict Y as some function of the linear combination of X, okay? But you don't require your link function to be, to have the exponential family structure. Currently we do, but I think this can be extended definitely. But how to extend, essentially how to make a non-asymptotic version of our asymptotic result, which doesn't assume any structure, any conditional structure, as you have seen, right? There were no X, whatever, no X and Y. This I don't know. This I don't know. And actually, I think that there might be some lower bound saying that for this restricted setup, things are not as nice. So I don't have exact results, but let me say that there are some issues when you try to do adaptation, for example. So when you don't know the variances, in the case of linear models, your adaptation procedure, there is actually a catch which I didn't mention. In the case of linear models with specification, with the right specification, you can easily adapt to the unknown different variances of the additive noise. But it turns out in the generalized linear models, doing a similar thing actually requires you to be able to resample the noise once, conditional on the design, which is a strong assumption. So there are structural, what I want to say is that there are structural difficulties and things might not even be as nice.
Okay. So any other questions? Max, Nikita Pushkin, I think, that's a question. Nikita, do you have a question?
I think Nikita doesn't hear you.
Nikita, one second. Yes, no. I know that he is Pushkin. I'm trying to. I kind of learned it already, but okay, that's fine. Any questions, guys? I'm happy to discuss. Fine, it's yeah.
Okay, so thank you very much. Good.
What about the recording though? I don't know how to stop it. I never recorded myself, honestly.